Welcome to my talk. My name is Marie-Christine Jacobs and I'm going to present the PEG-check approach. PEG-check is an approach to check whether two programs are functionally equivalent. Its peculiarity is that it checks the code segments that were changed in isolation and thereby consider their context. Let us start with the motivation for functional equivalence checking. We look at one particular scenario for program refactoring, namely program parallelization, which is the motivation for our work. So today's devices contain multi-core CPUs. And to efficiently use multi-core CPUs, we require parallel programs that can be run in parallel on the multi-core CPUs. So program can use the different CPUs together. Unfortunately, many programs are still sequential, so they don't use the multi-core CPUs efficiently. In addition, writing sequential programs is much easier. So therefore, developers start with a sequential implementation of the program and then later continue to develop a parallel program, so basically parallelize the sequential implementation. So to get the desired parallel programs, it is a common task to parallelize the sequential program, and one opportunity to parallelize a sequential multi-threaded program, especially a C program, is to add so-called OpenMP directives to the program, and well, parallelization via OpenMP directives is the motivation for our work. So we have an original program and we perform a refactoring which changes the original program into a refactored program. And this change, whatever the refactoring does not automatically guarantee that the refactored program is correct. So there are several reasons why a refactoring may threaten the correctness of a refactored program. So for example, we could have done a manual refactoring and just did something wrong there. We could have used a tool which itself is not correct, so it's buggy, and may introduce an error in the refactoring process. We might use a technique that is not proved, so that even does not guarantee that the refactoring works correctly, or we applied a refactoring rule although we violated a precondition. So as you see, there are several reasons why a refactored program might not be correct with respect to the intended specification. So the question is the refactored program indeed correct with respect to the specification? Therefore, the goal should be to inspect whether the refactored program is correct with respect to its specification. Unfortunately, to check this, you need some kind of specification, some formal specification that describes what is the specification of the program, and often that is not available. However, the original program is often tested well, and we are confident that the original program fulfills this specification. So what we can do, although we don't have a formal specification, we can check whether the refactored program is as correct as the original program, and if the original program was correct with respect to the specification, also the refactored program will be. This leads us to the refined goal of checking functional equivalence between original and refactored program. So what does it mean, functional equivalence? So original and refactored program need to compute the same output when they are given the same input. No matter what the input is, the computation should still result in the same output. So the outputs may be different for different inputs, but both programs should still provide the same output for a given input. Now let us have a look at how PEG-check achieved this goal. With PEG-check, we want to check whether original and refactored programs are functionally equivalent. And PEG-check consists of three phases we see here in the picture. To become context aware, PACTcheck starts with a variable classification, and this variable classification, for example, detects modified variables, variables relevant for the result, and variables that are directly input dependent. After the variable classification, PACTcheck uses the information of the variable classification during its translation of the equivalence problem into a verification task. And then in a last step, it can use a standard verification tool to verify the generated tasks. Remember from the title of this talk that we want to have a localized approach. So what does this mean? In our case, PACTcheck generates one verification task per refactored code segment. In the context of parallelization, a refactored code segment is just a section of your code which has been parallelized. And we already explained that we use the variable classification to achieve context awareness in the encoding. At last, we want to mention that we manually proved that PACTcheck is sound. So this means that PACTcheck only reports original and refactored program are functionally equivalent if they are indeed functionally equivalent. We start with looking into the variable classification. And the task of the variable classification is to find out which variables are used in the code and how. And therefore it uses two analyses, a definition use analysis and a live variable analysis. Our variable classification thereby distinguishes whether a variable is modified in the code segment, whether modified variables are live afterwards, meaning their result is used, and whether modified variables may be used before they are defined by the code segment. This means they are input dependent. We use this information for the encoding. For example, to avoid that the code segments of original and refactored program interfere, we need to copy modified variables. Moreover, read-only variables need to be initialized. And also variables that are modified but may be used before definition need to be initialized. But since we're copying them, we do not only need to initialize them with an arbitrary value, but we also need to ensure that the copy and the original variable gets the same input value. Finally, we need to check that modified variables that affect the output, so that are live afterwards, have identical values. If a variable is not live afterwards, it's more like a temporary variable, and then it has no effect on the output, so we don't need to check equivalence there. In the following, we perform variable classification for the following program and its parallelization, which we will see in a moment. So let's have a look at variable classification for the code segment highlighted in gray here. First, we identify that the code segment modifies variables I and t. So you see, for example, the initialization of the for loop assigns variable I, and the loop body here assigns variable t. In contrast, we see that variable n is only used in the test expression of the for loop, so it is not modified. Now let's have a closer look at the modified variables I and t. We see that t is used in the return statement, so it is live afterwards. In contrast, variable I only occurs in the code segment itself and never occurs afterwards, so it's not live afterwards. And now let's have a look at whether variables are used before definition. And there we see that in the loop body we have a statement that assigns t with the value t times I. So this means t is actually used before definition in this case. In contrast, the first thing our for loop does is to initialize variable I with value 1. So it's not used before definition. Next, we see the parallelized program where we just added an OpenMP directive allowing us to execute the loop iterations in parallel. So again, since this is basically the same program plus the OpenMP directive, we see that variables I and t are modified. Variable n is not modified. Again, we identify that t is live because it's used in the return statement. In contrast, I is never used after the loop. And we've seen the similar statement assigning t, and this is the only assignment to t. So we have a use of t before it's defined, while the parallelization ensures us that at the beginning of the loop iteration it assigns loop counter, this I variable, to the value of the loop iteration. We don't need to define it before we use it because this is always ensured. So we've now done the classification. What does this mean for the encoding? So we've modified int, so this means we need to copy int at least for one of the programs, while we can safely share the non-modified variable n. Moreover, read-only variables, which is n, need to be initialized, and also variables that are used before definition and are copied, so the t. And in addition, as we will see, we also need to ensure that the original and the copied variable for t get the same value. Finally, we need to look at the output, and there we see that, well, t is the only variable that is modified and live afterwards, so we need to check output equivalence for variable t. After we clarified the variable classification, we continue with the next component of PEGCheck, the encoding component. And now we present how the encoding component is used to encode the equivalence check as a program verification task. Similar to other approaches, we perform 4 steps. First, we have an initialization and equalization step, which ensure that our verification task provides any input value to the variables, and it ensures that original and copied variables get the same values. Then we execute the original code segment and the refactored code segment, and at the end we compare the outputs. The main difference to existing approaches is that our encoding is localized, so this means we apply it to code segments and not to whole programs or functions. In addition, we become context aware due to the variable classification we just seen before. In the following, we demonstrate the encoding idea based on the examples from the previous slide. So we start with adding the original code segment, followed by the refactored code segment, so the parallelization in this case. Next, we need to introduce the copies for the modified variables in the original code segment. And remember, for our examples, we identified that variables I and t are modified. Thus, in the original code segment, we now use copied variable is for I and ts for t. Note that we decided to use copies for the original code segment and not for the refactored code segment, because thus we can avoid that we adapt OpenMP directives, which just make the encoding more simple. After we added the code segments and performed the renaming, we can then introduce the necessary variable declarations and then continue with initialization. So the read-only variables need to be initialized as we've shown on the previous slide. And in our example, we had the read-only variable n, which is now initialized with a random integer value here. In addition, we have to initialize modified variables that are used before definition. And this was variable t in our example. So we initialize the copied variable ts with a random value. However, we also need to ensure that the input stays the same, so we cannot initialize t with an arbitrary value, but we need to ensure that it's the same as we used for the copied variable. So that is why we assign, in this case, the value of ts to t. Finally, we have to perform the output comparison. And therefore we insert an assert statement for each modified variable that is live after the code segment. And this assert statement checks whether the outputs have identical values. So in our case, we can simply check if the values of copied an original variable for t, so the only variable which is modified in our example and is also live afterwards, have identical values. And then verifier can then check whether the assert statement is violated. At last, the verifier checks that no verification task violates an assertion, and if this is the case, it reports functionally equivalent. At last, we present our evaluation results, and therefore we use the environment specified in the first row of this table. We evaluate our PACT-check approach with two scenarios. The first scenario looks into OpenMP parallelization, which was the motivation for our development of PACT-check. However, PACT-check is not restricted to parallelization, and therefore we have a different scenario here that looks into refactorings of sequential programs into sequential programs again. For both scenarios, we use an implementation for the variable classification and encoding, which we integrated in the framework for equivalence checking. However, the setup for the verifier and the considered task differ for the two scenarios. So for the OpenMP parallelization scenario, we use the existing verifier Civil together with SMT Solver DATS3, and we looked into tasks from the functional equivalence verification suite. While for the second scenario, which only looks at refactorings that consider sequential programs and the result in sequential programs again, and here the verifier is a sequential verifier for sequential programs, CPA checker, and we look into examples used in another paper that presented an approach on functional equivalence checking. So now let's have a look at the evaluation results. First, let us inspect which task PACT-check classifies correctly, incorrectly, or fails to classify. First of all, we look into the first two rows, correct equivalence and correct inequivalence, which show whenever PACT-check reports a correct result. And we see that we have non-zero entries for these two rows in both scenarios. So in both scenarios, PACT-check was able to give correct results. So it correctly detected inequivalences and equivalences. So now let's continue with the third row, incorrect equivalences. And we see that we have 0 entries for both scenarios. And this is good because an incorrectly reported equivalence means that PACT-check would report equivalence although the programs are inequivalent. And we already reported that, well, this shouldn't be the case because we manually proved that PACT-check is sound. So in theory, that should not occur. And now we can also see for our example, this is indeed not the case. So on our example, PACT-check seems to be sound. However, let's have a look at the last two rows. And what we see is that we report an inequivalence, although the original and refactored program are indeed equivalent. And we might report unknowns. So what we conclude from this is that PACT-check is incomplete. At last, we want to investigate whether localization is beneficial. And therefore, we compare PACT-check with localization, so that are the columns seg in this case, against PACT-check with whole program analysis, so the columns all. And now that is possible with PACT-check because we can provide what are the code segments So in our table, we highlighted those numbers which performed better in the respective category and scenario. So for correct equivalences and correct inequivalences, it's better to report larger values. And we see that indeed in the case of our two scenarios, the localization reported a higher number of correct equivalences and inequivalences. Looking at the third row, we again see that we have 0 entries, which is nice because also no matter how we chose our code segments, we did not report an incorrect equivalence, so we still seem to be sound. Finally, let's get to the last 2 rows, and we see that, well, the SEC, so the localized configuration, reports lower numbers, which is better for unknown, because this just means we more often give an answer. However, we also see that in the incorrect inequivalences, we have a 0 entry for the second scenario in the whole program configuration, while in the localized configuration we have a value 2 here. However, note that the whole program analysis fails for those tasks which are reported incorrectly equivalent in the localized configuration. In general, we looked at our data and found out that the whole program analysis only solves tasks that are also solved by our localized PEGCheck configuration. Thus, we conclude that localization is often beneficial. Nevertheless, we want to report on one exception we observed in our evaluation, and this is the bug 15 task from the second scenario, which refactored sequential programs into sequential programs. And here you see that both configuration, localized and whole program, were able to correctly detect the equivalence. However, the localized checking took much longer. And in this case, the whole program configuration profited from the fact that the input to the code segment was restricted. Summing up, we presented the PEGCheck approach. Here you see the overview again. And PEGCheck is an approach for localized functional equivalence checking that uses variable classification, so the first component of this sequence, to take the context of refactored code segments into account. PEGCheck is proven sound. However, if you remember our evaluation, we showed that it's incomplete. But this is no surprise, since functional equivalence checking is undecidable and we cannot be sound and complete. The variable classification and the encoding component are integrated in the framework for equivalence checking, and for the verification component you can just choose an arbitrary verifier. Our evaluation demonstrated the feasibility of our PEGCheck approach, so we were able to correctly identify equivalent and inequivalent programs, and we also showed that localization is mostly beneficial, except for this one case we've seen in our evaluation. Moreover, we would like to remark that we created an artifact that contains our evaluation data and allows you to reproduce our results.
Yeah, I think so. I don't see you anymore.
Yeah, so we're on air.
So you are live. No, we are live in 5 minutes. This is what they say.
No.
Are we live?
Yes.
Okay, so thank you everybody, and thank you, Marie-Christine, for your very nice presentation. Thank you, Ross, for confirming this. I don't see any question in the chat, but I invite everybody who attended to Marie-Christine's very nice talk to ask any question in the chat. And while I'm waiting for the question, I'm gonna move and ask my own question. I put it also in the chat for everybody to see, but my question is if you can explain a little bit how are the segments are identified and their impact on the presented approach. And yes. I forgot now in my my text.
So for the original idea where I came up with this approach, where we had this idea of we want to parallelize some of the a sequential code, it's quite simple because it's just the parallelized code, and I had OpenMP pragmas there, so I can simply check the pragma and how long they are valid, and then I can just build my segments around manually, and that is something you could easily do also automatically, I would say. So, but I haven't done this because it's only a prototype. For the sequential programs, it's a little bit more tricky because I've seen if I do it straightforward and say, oh, here's a syntactic difference, and then there is some code which is equivalent again, then I likely end up in segments which are not equivalent on the different versions, and I had to do more likely look some context and how they are used. And for sequential programs, I would say it's difficult to do this automatically, and it's better to have a developer who has some idea of what he or she wants to change and what is the influence on the a complete program. So which part one should consider to be equivalent and changed.
Thank you. So let me follow up a little bit on this. So you said in the sequential case, you would need it would be better to have expertise, right? And so how would you consider this impact on the feasibility, right? Like, how do you think that these manual requirements could impact to the approach, and how do you think it's realistic to imagine that there are that there is this need?
So I think what one could always do is to just use the function as a boundary, which other approaches also did. But I wanted to be more precise, or closer to the change, and that is why I had this manual idea. But I think if one has no idea what would be a good segment, then one would be safe to just choose function boundaries at the beginning and the end of the code segment, and then this should work as well. But one might have actually more important or more code than one would need to look at.
Thank you. I actually don't. Okay, I have a question. Okay, I see another question, and it's from Ali. I don't see raised hand, so let me ask you the question. So the question is, if the issue is to ensure that if the original program done so, it is refactored program, then equivalence is the wrong criteria. It is sufficient but necessary, and better choose requirements. So I don't know what is exactly the question, but this is kind of you want to comment on this sentence from Ali. And Ali, if you wanted to be added and talk about this with Marie-Christine, you should raise your hand. This is my understanding, and I can add you. But of course, you can also talk to Marie-Christine later on in the discussion. But yeah, okay, he raised his hand. Oh, I think you wave and you didn't raise the hand on the top right of the screen. No.
So just maybe let me give a short answer. So I looked into equivalence because this is more or less more convenient in this regression verification idea where you change your program and check the modifications. So it was more convenient to look into equivalence than